class today, we motivated and derived a formula for the Fourier series coefficients of an arbitrary 2π periodic function. In this video, we'll give a specific example by calculating the Fourier coefficients for a square wave function. Recall from class that the standard square wave is given by the function whose value is 1 over the interval 0 to pi and -1 over the interval from pi to 2π. Also recall that the formula for the nth coefficient in the Fourier series is Cn, given by 1 over 2π times the integral 0 to 2π of e to the negative int times the function we're calculating a Fourier series of. When you're given a function that is defined piecewise and given different values of that function over different intervals of definition, the easiest way to proceed is by breaking up the integral into regions where you know the value of s. So over the interval from 0 to pi, s takes on the value of 1, and over the interval from pi to 2π, s takes on the value of -1, and hence we can make the appropriate substitutions. If we now use the fact that the integral from a to b of e to the negative int is -1 over in times the difference of these other two exponentials evaluated at the endpoints, then after some simplifications, you can hopefully verify that all this simplifies to 1 over 2n pi I times a term in parentheses which involves e to various exponents, most of which involve something times pi. I would like you to pause here and make sure you can derive this formula for yourself. But what we're going to be doing is we're going to be investigating what is going on with these exponents. What do these functions e to the negative in pi look like for different values of n? Noting that in one of them, I will cycle only through even values of n, given by 2n here, but in the others I will be alternating between n as even and n as odd. To get an idea about what's going on with those terms in parentheses, let's recall that from Euler's formula, e to the negative ix is basically the point cosine negative x, sine negative x. If we're just purely looking at e to the negative in pi, then what we're doing is we're looking at points that alternate as I go from even n to odd n, from one end of the circle, the unit circle, to the other. One end to the other, one end to the other. In other words, e to the negative in pi is going to alternate between the values of 1 plus 0 times I, which is just 1, and -1 plus 0 times I, which is just -1. Hopefully this last MATLAB demonstration convinces you that e to the negative in pi alternates between the values of -1 and 1 depending on whether n is odd or even. So if we return to the expression we had in our calculation of the Fourier series coefficients for the square wave, we can see that the terms in parentheses will take on different values depending on whether n is odd or even. This means that we need to break up our calculation at this point into two different cases. The first case is when n is even. If that's the case, note that the terms in parentheses are going to be 1, 1, 1, and 1, which means that the whole coefficient Cn simplifies to 0 in this scenario. When n is odd, in contrast, note that the terms in parentheses will be 1, -1, 1, and -1, which obviously equals 4, and hence the coefficient Cn will end up being 4 over 2n pi I when n is odd. What does this all get us? Well, recall that the goal of Fourier series coefficients is trigonometric approximations. In particular, we wanted to know how can we approximate the square wave function by a finite sum of sinusoidals. Now we know that in order to do so, we should choose the coefficients of the nth degree term as 2 over I pi n when n is odd and 0 when n is even. If we further break apart this sum by grouping together the positive and negative terms, you'll notice that we start to see something familiar happen. For example, if we look at the terms when n is 1 and -1, respectively, I get 2 over pi times I, e to the it, minus e to the negative it. Similarly, when we group together the terms when n is equal to 3, I'm going to get 2 over 3 pi I times e to the I times 3t minus e to the negative I times 3t, and so on. If you recall the trigonometric Euler identity that 1 over 2 pi e to the ix minus e to the negative ix is always sine x, then notice that each of these terms in parentheses here can be rewritten as a simple sine multiplied by 2i. So, after some further simplification, the i's will cancel, and we'll end up with 4 over pi, excuse the random mark there, 4 over pi sine t plus 4 over 3 pi sine 3t plus 4 over 5 pi sine 5t, etc., for however many terms I want to get. This is where we start to see things come together like in a Quentin Tarantino movie, because this was the exercise that you had back in homework number 2. In that exercise, you calculated all these funky sums of sine functions with different oddly chosen coefficients, but notice that those coefficients now are exactly the ones that we drove as the c sub n in our trigonometric expansion for the sine square wave function. You might also notice that in our picture that we got from that second homework assignment, it kind of does look like a square wave if you ignore the massive squiggles. In fact, if we include higher order terms in our approximation, you can see this one goes up into order 100 here. You can see that the black squiggly line is almost right on top of the square wave function, except in these corners here.